Now we look at the full wave rectifier. What do we need to do to take advantage of using the entire sinusoidal input on a diode rectifier? The difference between full wave and half wave rectification is that a full wave rectifier allows unidirectional current to the load during the entire input cycle, and half cycle rectifier allows only this during one half of the cycle. So we're going to try to use both cycles, positive and negative. The result of the full wave rectification then is a DC output voltage that pulsates every half cycle of the input, and we can see that in the diagram here. There's our full wave input, there is our rectified output where we're taking advantage of every bit of the waveform. So the average value then for a full wave rectifier output voltage is twice that of the half wave rectifier. So we use almost the same expression here, except we're doubling the peak output. We use 2 over pi, which is 0.637, so 63%. Then you can calculate the average then of the full wave rectifier. So 63% of VP then becomes the action that we're looking for. So if we take a look at this example here, find the average value of the full wave rectified output voltage. So we have a 15 volt output. We want to determine what the average is for that. So the average then becomes 2 times 15 volts divided by pi. I'm not sure here, but it's very possible that they didn't carry the 2 in the formula here. So don't forget to put the 2 in there. So 2 times that divided by pi gives us 9.55 as our full wave rectified output. So what kinds of things can we do then to make things even better, even more smoothly? Well, what we can do is we can put a transformer in between the rectifier and the source. So a center tapped CT full wave rectifier uses 2 diodes connected to the secondary of a center tapped transformer. The input signal is coupled through the transformer, so it's not a direct connection, it's coupled through the transformer on the secondary. Half of the secondary voltage appears between the center tap and each end of the secondary winding. So you can see here what we've got. We've got a primary winding on the source side, we've got a center tapped secondary winding on the rectifier side, and you can see what's going to develop here. We have the voltage on the secondary in half, the voltage on the secondary in half on either side of the tap, and the current then will flow through the diode once the diode has been biased properly by the alternation in the circuit. For a positive half cycle of the input voltage, the polarities of the secondary voltage are as shown. This condition forward biases the upper diode, D1, okay, so up here, and reverse biases D2. So 1 is on, 2 is off. For a negative half cycle of the input, the voltage polarities on the secondary are as shown in the diagram. Okay, so we've got diagram A, diagram B. Okay, so let's go ahead and scroll up here. Okay, so we can see what's happening here during the first alternation, the positive alternation, the current flow once the diode is triggered into conduction, and we get our output V out, the positive. Okay, so this condition forward biases and reverse biases D2. The current path is through D1 and the load resistor as indicated. For the negative half cycle of the input voltage, the voltage polarities on the secondary are as shown. So we look down here at the drawing number B, schematic number B. Now we've got D1 in reverse bias, shut off, and D2 in conduction. So this condition reverse biases D1, forward biases D2. The current path then through D2 and RL then during the negative cycle, half cycle. Because the current during both the positive and the negative portions of the input cycle is the same, in the same direction through the load, the output voltage then developed across the load is a full rectified DC voltage. So you can see we get a positive pulse every time. The output voltage is determined by the turns ratio of the transformer, that value N. So we're back to a little bit of our transformer theory. Most transformers will have the output voltage written on the transformer, but keep in mind that the reference for a full wave rectifier is the center tap, which means that the peak output voltage is 1/2 of the peak secondary voltage. If you don't know the voltage, but do know the turns ratio of the transformer, you can calculate the peak output voltage for a full wave rectifier from the following equation. So N times VPN divided by 2. Assuming the fuse drops no voltage, the primary voltage is the same as the input voltage. To obtain an input voltage with a peak value approximately equal to the input peak, use a step-up transformer with a turns ratio of 2. In this case, the total secondary voltage is twice the primary voltage. So the voltage across each half of the secondary is equal to the input or the primary voltage. So let's look at an example. Frequently, you will need to specify a transformer based on an RMS input voltage and a peak output voltage. Specify the turns ratio and type of transformer required for a full wave rectifier if the input voltage is 120 volts RMS and the required output is 17 volts peak. So we're going to do a little bit of our conversions here between peak and RMS. So the input peak voltage then is VRMSN divided by 0.707. Okay, we've seen that before. 120 volts by 0.707 gives us 170 volts peak. So now rearranging the relationship in 16.4 and substituting, so now we're going to take the value we got up here at the top of the page, move things around. N now is equal to 2 times V peak out divided by V peak in, and you can see that the voltages are going to cancel out. We're going to left with N as just a number. So 17 volts divided by 170 volts, multiply that by 2 gives us 2/10. So thus the center tapped step down transformer with a turns ratio of 0.2 is going to be required. So what does the peak inverse voltage look like on a full wave rectifier? For simplicity, ideal diodes are used to illustrate the peak inverse voltage in a full wave rectifier. Each diode in a full wave rectifier is alternately forward biased and then reverse biased, okay, just like we saw in the previous example. The maximum reverse voltage that each diode must withstand is the peak value of the total secondary voltage, V peak secondary. When the total secondary voltage, VP secondary, has the polarity shown, the anode of diode 1 is plus VP secondary divided by 2. And the anode of diode 2 is minus VP secondary divided by 2. Since D1 is forward biased, its cathode is the same as its anode, VP secondary divided by 2. This is also the voltage on the cathode D2. The total reverse voltage then across D2 is VP secondary divided in half minus VP secondary divided in half, which gives us VP secondary. Since VP out is equal to VP secondary divided by 2, then VP secondary equals 2 times the VP out. Okay, so we're just moving we're just moving terms around. For either diode, the peak inverse voltage in terms of the peak secondary voltage is VP secondary. Combining the two preceding equations then, the peak inverse voltage across either diode in the center tapped full wave rectifier in terms of the output voltage then is 2 times VP out. Okay, so those relationships there we are combining to get our relationship. So let's take a look at this example and then we'll stop this one. For ideal diodes, show the voltage waveforms across the secondary winding and across the load resistor when a 120 volt RMS sine wave is applied to the primary winding in the figure. What minimum peak inverse voltage rating must the diodes have? So we've got 170 volts peak on the input. We've got a 1 to 2 turns ratio and an output taking across a 10k ohm resistor. The peak input voltage then, Vn, is equal to V peak primary. So 120 volts divided by 0.707 gives us 170 volts peak. So if we apply equation 14.5 to calculate the peak secondary voltage, the equation can be applied as long as both voltages are in the same form. To emphasize this, the letter P is added to the subscripts indicating peak values. Okay, and this is just like we've seen before with peak and peak to peak values. So V peak or primary is the V peak of the secondary is equal to the number of turns times V peak of the primary. So we got peak on both sides. So 2 times 170 gives us 340 volts. So if we apply equation 16.4 to calculate the peak output voltage, V peak output then is equal to the number of turns times VPN divided by 2, and we're back to 170 volts. Notice that VP out is referenced to ground, but VP secondary is not. The waveforms are shown in the next diagram. So there's our diagram. So we've got our peak values here, 340 volts, and our peak value here, 170 volts. So if we calculate the minimum peak inverse voltage for each diode by applying equation 16.5, PIV, the voltage is equal to, peak inverse voltage is equal to 2 times VP out, which we're back to 340. It seems like we're going in circles here, but with the mathematical relationships, that's how it works. So in the next section, we'll look at another animal here where we deal with 4 diodes that are biased such that, again, we get a full wave bridge rectifier.